Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. The shapes of simple molecules and ions. So we're going to use valence shell electron pair repulsion theory to determine the shapes and bond angles within simple covalent molecules and ions. So the assumptions that we're going to start with, from which all our conclusions are drawn, are that electron pairs, that is bond pairs and lone pairs, because they're negatively charged, will repel each other, and they will repel each other to get as far apart from each other as possible, hence minimizing repulsions. Lone pairs repel more strongly than bond pairs. We will possibly come up with some simple explanation of that as we go through the lesson. We treat multiple bonds as single bonds. So a double bond is treated as if it was a single bond with the same repulsive effect as a pair of a single bond pair. Now, to determine the shape of molecules, we need to apply those assumptions to dot and cross diagrams of the covalent bonding involved. So let's take an example that has two bond pairs. Beryllium dichloride. Could you draw a dot and cross diagram for beryllium dichloride? Okay, so moving on, there is our dot and cross diagram. What we're principally interested in is the electron pairs around the central beryllium atom. So I'm just going to focus on those just for the purposes of this slide. And you can see that the two electron pairs, bond pairs, so these are both bond pairs, we've got two, they're going to repel to get as far apart as possible. And that's going to result in an arrangement where the two chlorines are on opposite sides of the beryllium, and we would describe that arrangement as linear. Now the bond angle, I hope we don't need too much explanation. So the bond angle is this angle here. Obviously that's 180. So any molecule in which there are two bond pairs around the central bonding atom, okay, will adopt a linear shape, and the bond angle will be 180. So let's look at the shape and bond angles, the geometry, where there are three bond pairs around a central atom. For instance, boron trifluoride. So boron has 3 electrons in its outer shell. Could you complete the dot and cross diagram for boron trifluoride? Pause the video, come back when you are ready. Okay, so the boron trifluoride as a dot and cross diagram looks like so. Now, what we're interested in is the numbers of electron pairs around the central boron atom. So here's my central boron atom. I'm only interested in this electron pair, and this electron pair. So I've got 3 electron pairs, 3 bond pairs around the central boron. Now these will repel to get as far apart as possible. hence my diagram where they are as far apart as possible. Now, if you may have used modelling kits, you will have made a model like this, which is slightly more helpful because you can see that the arrangement is planar. All atoms are lying flat on the one piece of paper, but the bond angle will simply be 360 divided by 3. So we call the shape trigonal planar, planar referring to the fact that, as you can see on the model, they're all lying on the same plane. Trigonal, we've got three points there. And the bond angle, of course, is 120, achieved by dividing 360 by 3. All. So, give you a problem. Carbon dioxide, deduce the molecular shape and the bond angle. The method: start with the dot and cross diagram, determine the numbers of pairs of electrons surrounding the carbon, deduce the shape and the bond angle. So pause the video, complete that task, resume when you're ready. Okay, so here is a dot and cross diagram for carbon dioxide, and you can see that there are 2 double bonds either side of the carbon, but we treat, one of the assumptions, we treat a double bond like a single bond. So this would be 2 bond pairs around a central carbon atom, which is just like beryllium dichloride, our first model. So if we look at carbon dioxide, we'd arrange carbon dioxide in a linear fashion with a bond angle of 180. And if we make a model of it, we can see that that confirms. So our modelling kits do actually reveal the shape of the molecule using this theory. So here is another problem, methanal. Could you deduce the molecular shape and bond angle in methanal? If you're not familiar with that, it's a carbon-oxygen double bond, carbon-hydrogen. So there's a carbon-oxygen double bond in methanal. So pause the video, dot and cross diagram, deduce the shape and bond angle, and of course name the shape. Okay, so here is the dot and cross diagram, starting with carbon. We've got methanal. We're going to treat the double bond. The double bond here is going to be treated as a single bond, so we have 3 bond pairs around the carbon. So that will be like our boron trifluoride model. So trigonal planar with a bond angle of 120. If we make a molly-mod kit of that, we can see that that also shows us a trigonal planar shape. Okay, so let's look at the geometry of 4 bond pairs. So we're going to take an example, methane. I'm going to model this for you. I'm going to start with the dot cross diagram. So 4 bond pairs. But I'm going to move straight to the molly-mod here, so that you can see that this is a 3-dimensional structure. So if we look at the 4 points of that shape, we'll see that it's 4-sided, so that is a tetrahedral, and geometry tells us the bond angle in a tetrahedral is 109.5. So you have to be able to reproduce that name and that bond angle. We would represent that in a particular way. This bond and this bond are on the plane of the paper. The bond getting larger as it gets towards the hydrogen is designed to say that the bond is coming out of the page, and the dotted line here is telling you that the bond is going behind the page. So to represent this structure, we need to use this structure, this technique of drawing 3 dimensions, and you're expected to be able to do that reliably and accurately. So the geometry for 6 electron pairs, let's take sulfur hexafluoride. So again, I'm going to model this for you and give you a problem on the next slide. So here is sulfur hexafluoride. Here's sulfur, 6 electrons in its outer shell. So 6 covalent bonds with 6 fluorine atoms. Now, if I draw a structure for this, it must reflect the molymod, or the model kit, which you may or may not have used yourself, but I think it's worth looking at here. So what we've got is, in the centre here, 4 of the fluorines in a square and in the same plane. So these 4 fluorines are form a square, the points of the square, and are in the same plane. We've got 1 fluorine above the plane of that square and 1 fluorine below. Now, joining the points would form an 8-sided geometrical shape, and that is an octahedral. The bond angle within for each and every one of those is 90. So how would we represent that using the technique of the previous slide? Well, we see here that we've got 2 bonds going out behind the page and 2 sulfur fluorine bonds coming out in front of the page, and 2 sulfur fluorine bonds on the plane of the page. So this bond angle here is 90, but so is this. That is also a right angle, so that is also 90. So although there are 2 areas where you will find perhaps different bonds, they're not. They're in fact the same. The bond angle is 90. So here are 2 problems. Phosphorus hexachloride and silicon tetrachloride. Could you determine the shape, name the shape and the bond angles for those 2 covalent molecules? Start with dotted cross diagrams. Look at the numbers of electron pairs around the central atom, determine the shape and bond angle. Pause the video, come back when you're ready. Okay, so let's start with phosphorus hexachloride. Here is the dot and cross diagram. We've got 6 chlorines surrounding the central phosphorus. An additional electron here makes up the octet for the chlorine atom at the bottom. So we've got 5 phosphorus has got 5 electrons in its outer shell. So the 6th bond, the 6th phosphorus chlorine bond, is a dative covalent bond, and the octet is made up by an additional electron, as indicated by the negative charge. So what does that mean in terms of shape? Well, we've got 6 bond pairs, so that's going to be like the model sulfur hexafluoride. So we're going to have an octahedral arrangement with a bond angle of 90. Okay, now if you've got that correct and you're confident about your silicon tetrachloride, we'll just reveal in one moment. If not, pause and have another go at the silicon tetrachloride. Otherwise, here is the 3-dimensional drawing for silicon hexachloride. It's tetrahedral. There's 4 bond pairs surrounding the central silicon. So that's a bond angle of 109.5. So far we've been dealing only with bond pairs, but we also need to take into account the effect of lone pairs. Now, not only do we need to count them as an electron pair around the central atom, but we also need to know that lone pairs of electrons repel more strongly than bond pairs, so we apply that assumption. So I'm going to model one example, ammonia, NH3, and then on the next slide I'll give you a problem. So nitrogen, as we know, has 5 electrons in the outer shell. We have a pair and 3 unpaired electrons. So the electron shell diagram for dot and cross diagram for ammonia looks like so. So we've got 3 bond pairs and 1 lone pair around that central nitrogen atom. So 4 pairs of electrons will occupy the positions of a tetrahedral, but we don't include in our shape pairs of electrons. The pairs of electrons here act to repel these 3 bond pairs, but they are not part of the shape of the molecule. So if I look at a molymod of ammonia, NH3, you'll see that we don't have anything for the electron pair. It's just a nitrogen and 3 hydrogens. So we need to describe the shape of that molymod. And we can redraw it in that fashion, and we can see therefore that it's pyramidal with 3 points to the base, so it's a trigonal pyramid. Now we would base our bond angle on the fact that we're going to look at this shape here. So what is this bond angle here? Well, the lone pair repels more strongly than a bond pair in methane. So these 2 bonds are squeezed together slightly, so the bond angle is not 109.5 as we might expect, but is in fact 107. So the effect of the additional repulsion due to the lone pair is to squeeze the nitrogen-hydrogen bonds together slightly, reducing their bond angle to 107. So again, looking at the effect of lone pairs, consider water. So I'd like you to determine the shape and bond angle in a water molecule. You'll need the dot and cross diagram, and then to take into account both bond pairs and lone pairs to determine the shape. So pause the video, come back when you are ready to check your answer. Okay, so revealing the dot and cross diagram, we see that water, H2O, has got around the central oxygen atom, we've got 2 bond pairs and 2 lone pairs. So again, we're working off, in terms of electron pairs, the shape adopted by 4 electron pairs, which is tetrahedral. However, when we make a molymod of water, we don't include electron pairs. So exactly the same when we talk about the shape. We're just interested in the shape formed by the atoms. So the shape formed by the atoms is V-shaped or non-linear. And the bond angle, 104.5. This time we have 2 pairs of electrons, 2 pairs of lone pair, 2 lone pairs of electrons, sorry, squeezing the oxygen-hydrogen bonds together. So ammonia, the bond angle was 107. Here we've got double the effect, so the bond angle is assumed to be 104.5. So a couple of problems to finish with. Predict the shape and bond angles for these 2 ions, CH3 plus and CH3 minus. If you want to try the CH3 plus first, and then we can move on to CH3 minus. So pause the video and continue when you're ready. Okay, so CH3 plus, carbon has 4 electrons in its outer shell, so it forms 3 covalent bonds with hydrogen. So we've got 3 covalent bonds, 1, 2, 3 with hydrogen, so there are 3 bond pairs. Where's the 4th electron gone? Well, it's disappeared. That explains the positive charge. So the CH3 plus particle or molecule, or molecular ion is the correct term, has 3 bond pairs around the central carbon. Well, 3 bond pairs, think back to boron trifluoride. It's going to arrange itself as trigonal planar with a bond angle of 120. Okay, so if you haven't already done so, move on to CH3 1-. Pause and see if you can come up with the correct molecular shape and bond angle. Okay, so CH3 1-, we need the dot and cross diagram. So here, carbon again, we've got 1, 2, 3 bond pairs between carbon and hydrogen. We've got the 4th carbon electron, but we have an additional electron, hence the negative charge. So we've around the central carbon, we've got 3 bond pairs and a lone pair. So now we're looking at ammonia as our model. So we're following the shape of ammonia, the 3 bond pair and 1 lone pair model, and that of course gives us a bond angle of 107 and a shape of trigonal pyramidal. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.